On behalf of the INCampus project team, I welcome you to this presentation. My name is Strobel from PGMM. PGMM is the general planner of the Energy Center and the infrastructure of the INCampus. In the first part, I will give you brief information about the project and the energetic aspects. In the second part, Mr. Möll will take over and continues with more automation-related details. The INCampus is a joint venture developed by Audi and the city of Ingolstadt. On a brownfield of a former refinery plant, modern workspaces for research and development in high-technology branches are growing. The campus will provide up to 1 million square meter of gross floor space and count about 60 single buildings. In contrast to the former utilization, the project goals were to develop an outstanding, efficient, sustainable, and green environment, including a low-emission energy concept. Since the beginning of the design phase in 2016, the Energy Center, the infrastructure, and the first 3 buildings have been successfully constructed and commissioned. A strong environmental responsibility and the belief in a sustainable development guided the whole design process. Motivations are to take responsibility for the future, the reduction of carbon footprints, the demonstration of feasibility of new energetic concepts, and the utilization of digitization for energy concepts. Basic premises are the concept has to be future-proof, highly reliable, modular and flexible, and has to provide a high degree of autarky. Innovation premises are the usage of only high-efficient components, the minimization of losses, and the utilization of innovative components. The resulting design for the energy concept is indicated here. On the upper right side, we have efficient heat pumps, which cover the heat demand as well as the cooling demand of the buildings. They are connected to the low-X pipe system. Further connected to this system are all available heat sources on the upper left, as well as storage systems on the lower right. Environmental components are integrated on the lower left side and can act as energy sources or energy sinks at the same time. A general modular design allows the integration of additional heat sources, storages, or conversion technologies in the future. Let me explain general operation strategies with 2 examples. In summer, on the left side, the low-X system will reach high temperature levels because the heat pumps will mainly provide heat while they are cooling the buildings. That allows on the one hand to storage this heat energy and on the other hand an efficient rejection of surplus heat to the environmental sinks due to high temperature differences. In winter, on the right side, the low-X temperatures will be low because the heat pumps take energy from the system while heating the buildings. This allows to discharge energy from the storages and the usage of environmental energy from the sources. A maximization of environmental energy and the minimization of primary energy is reached by adapting the low-X temperature according to the current condition of the whole system. I think so far it became clear that the control of such a system is sophisticated. The complexity requires new approaches. 2 tasks are essential. We need to use dynamic predictions and forecasts regarding the upcoming energy demands in the future. Next is the ability to solve optimization problems for the development of operation strategies. The software for this task is currently in development. We named it CEC system, which stands for Cross Energy Concept. I hope so far you could get a basic understanding of the project and the energetic ideas. Now Mr. Möll will continue. Thank you for your attention.
Let me start by briefly introducing myself to you. My name is Ulrich Möll from LEA Lean Energy Services. I have worked for several decades in management positions at leading companies worldwide in the field of building automation. My responsibilities were in the areas of research and development as well as in sales. In addition, I have been leading the development and implementation of energy services for many years. My responsibility as a subcontractor of PGMM at INCampus was the specification and implementation support of a powerful and future-proof automation network based on OPCUA, as well as the specification of the cross-energy concept, the central optimization system of INCampus, which is currently in the implementation phase. I would like to start by saying a few words about which special requirements have existed and exist in the field of automation technology on the INCampus, besides all the standard requirements for building automation systems. Since the INCampus is being built and developed in several phases, there is a requirement that the automation technology must be able to integrate current and future technologies in a generalized and uniform manner. This was also to ensure that project planning and implementation in the various construction phases follow a uniform concept. The control and regulation of the building systems shall be based on industrial control systems, so-called programmable logic controllers. The operation and alarm management, the reporting as well as the analysis of process data shall be performed on a modern high-performance SCADA system. Local and mobile operating devices shall be able to access individual data points and process graphics of the SCADA system. In order to control the interdependencies of individual controllers, the data exchange between individual controllers is to take place via a so-called global data server. The cross-energy concept, which is based on artificial intelligence methods, is to guarantee low emissions and cost-efficient operation of the building systems at the INCampus, based on models and predictions. To accomplish this, the system must be able to intervene individual building systems processes by means of schedules. Optimal interaction of the various building devices and systems across multiple energy sectors, such as heating, cooling, electricity, etc., requires a uniform, future-proof, and secure communication, automation, and information structure. Let us first take a look at the communication structure. From the very beginning, there was a desire to use a single communication structure on the INCampus. This meant that it was clear that the office network operated by Audi IT was to be used. Hence, network management for all components connected to the office network is the responsibility of Audi IT. This also means that static IP addresses are not permitted for the programmable controllers. Instead, the dynamic assignment of IP addresses is carried out automatically by Audi IT on the basis of the DHCP protocol. The security specifications of Audi IT must be complied with. Now a few words about the automation structure. Here too, there is a campus-wide standardized automation network to which all programmable controllers, the central and local operator stations, the central optimization system, and the programming stations are connected. The use of certificates to allow and deny connections must be made available. The operational devices and systems are monitored and controlled by the programmable controllers. Special local devices such as blinds, meters, lighting systems are connected to the programmable controllers via special field buses, which are particularly suitable for the respective applications. Now to the information structure. For uniform exchange of information, it must be possible to develop an information model that meets both today's needs and openness for expansion to meet future needs. For this task, a variety of object types must be provided. These are, on the one hand, standard objects such as digital and analog inputs and outputs, and on the other hand, component objects for acquisition of devices, plans, and systems. Component objects can be, for example, pumps, valves, chillers, heat pumps, or even buildings. Before I talk about the structure of the building automation system on the INCampus, I would like to take a quick look at the structure of today's building automation systems. The system structure generally has three levels. The lowest level is the field level, which contains sensors and actuators, as well as application-specific controllers, for example, for room automation or for controlling individual devices or systems. The automation level with the automation stations or programmable controllers is located on the middle level. This level is used to regulate and control the building systems and devices. In addition, systems and devices can be accessed and monitored via local operator stations. The management level is located on the upper level and is used for central operation, monitoring, evaluation, and management of the building systems. The controllers of the automation level acquire the sensors, actuators, devices, and plans of the field level either via direct inputs and outputs or via dedicated field bus systems. The following technologies can be mentioned in particular as communication systems for the field bus level. In ocean, for communication with radio sensors and radio actuators. SMI for communication with blinds. DALI for communication with lighting systems. MBUS for communication with meters. IEC 61850 for communication with electrical equipment. KNX and LongWorks for communication with actuators, sensors, and application-specific devices and controllers of the field level, and finally Modbus for communication with selected devices and systems. The controllers of the automation level communicate with each other and with the devices and operator stations at the management level via a central automation bus. BACnet is primarily used as the communication system for the automation and management level. However, it cannot be omitted that LongWorks as well as Modbus, KNX or IEC 61850 will be used on the automation and management level. OPC is generally only used in the field of building automation for coupling with third-party systems or with SCADA systems. If we compare this with the architecture of the building automation system for the INCampus, we can see that the principle of 3 system levels consisting of field, automation, and management level is retained. However, it can also be seen that the system is limited to selected field bus systems and that OPCUA is used as the communication system for the automation and management level. The field bus systems used are SMI for blinds, DALI for lighting systems, MBus for meters, Modbus for devices and systems, and most lastly IEC 61850 for electrical systems. The main difference, however, is the use of OPCUA instead of BACnet for the communication of the automation and management level. I will go into the reasons for this at a slightly later stage. Let's now take a look at the architecture of the automation system on the INCampus. You can see that the automation network is integrated into the office network as required. The automation stations communicate with the SCADA system, the global data server, the cross-energy concept, and the programming stations via this network. For their part, the automation stations have contact with all field devices and building systems, either via direct inputs and outputs or via defined field bus systems. In addition, the cross-energy concept has the possibility to access the SQL database of the SCADA system and thus to obtain historical data that can be important for forecasting and optimization. The automation stations themselves do not exchange data directly with each other, but report their needs to the global data server, which in turn provides the desired information to them. This concept ensures that any impact on the system can be easily traced during maintenance or modification work. So why is OPCUA and not BACnet being used as the automation network on the INCampus? Network and data security was a core requirement for the automation network of the INCampus. However, network and data security was also one of the core objectives for the specification of OPCUA as a protocol for Industry 4.0 from the very beginning. Therefore, it was only logical to focus on OPCUA. In contrast to BACnet, OPCUA provides the cryptographic mechanisms required for a secure factory to safeguard communication. This is also confirmed by the investigations of the German Federal Office for Information Security, which systematically analyzed OPCUA communication with regard to the secure channel session and discovery services in accordance with the specification. This analysis did not reveal any systematic errors. Based on the analysis results, the OPC Foundation has further improved the OPCUA specification. Since OPCUA is an open standard that is not dominated by one manufacturer or manufacturer group, it offers customers the possibility to remain manufacturer independent. In addition, OPCUA offers the ability to connect multi-vendor networks across different deployment levels from the control level to the enterprise level. Furthermore, OPCUA makes it possible to define information models independently. That means without the involvement of the OPC Foundation, to release them for campus-wide use and to dynamically adapt them to expanded needs in the future. This special feature guarantees Audi high flexibility and productivity without loss of conformity to the standard. Last but not least, OPCUA is already being used in the industrial environment at Audi and thus fulfills the strategic group requirements for company-wide communication in automation technology. In summary, OPCUA is the right choice for the automation network on the INCampus. OPCUA is an open communication standard created for the requirements in the automation technology of the future. It is the standard for Industry 4.0, providing a variety of basic objects, methods, and communication services. It supports traditional client-server connections as well as publish-subscribe messaging, which enables the decoupling of information provider and information receiver. OPCUA offers the possibility to extend basic objects and methods individually. It uses an object-oriented approach to define information models. Additional information objects and methods can be defined in a project, industry, or manufacturer-specific manner in custom information models. These can be defined in a companion specification and, if desired, published by the OPC Foundation. OPCUA offers a high degree of interoperability. It is platform and manufacturer independent, has a service-oriented architecture and thus ensures a clearly defined flow of information between devices and systems from different manufacturers. Last but not least, OPCUA offers secure data exchange because it has a wide range of security-relevant encryption and administration methods. It thus offers a high level of protection against espionage, sabotage, and errors. The issue of reliability is also supported by its own redundancy concept to prevent data loss. Thank you for your attention.